Next, we'll look at coefficient asymptotics. How do we get estimates of the coefficients of the generating functions that are so easily obtained through the symbolic method? Fortunately, it's the case that we often can immediately get the coefficient asymptotics through general analytic transfer theorems. And we've already seen some examples of transfer theorems that work for a lot of cases. For example, Taylor's theorem is a transfer theorem. If you have a generating function f of z and you know its derivatives, then coefficient of z to the n in f of z is the nth derivative evaluated at 0 over n factorial. And for lots of functions, that's how we extract coefficients. That's how we get started with generating functions. We saw another example with rational functions, and we talked about that in generating functions lecture and also the asymptotics lecture. This is a special case, just for simplicity on this slide. If f of z and g of z are polynomials, then the coefficient of z to the n and the ratio of f of z to g to z depends on the largest root of g of the denominator. And if 1 over beta is that, then this expression gives the, it should be asymptotic of the coefficient of z to the n and the ratio of those two. Beta times f of 1 over beta divided by g prime of beta, beta to the n. The growth is like beta to the n, and that's the constant if that root has multiplicity 1. And we have a better formula, a more complicated formula that depends on the multiplicity if it's got higher multiplicity. So those are two examples of transfer theorems, and we use those. The one I want to talk about today, next, is what's called a radius of convergence transfer theorem. And that covers the problems that we've talked about today and many others. But actually, most of the transfer theorems that we use in real life are based on complex asymptotics. And we'll talk about those in a lot of detail in part 2. But the radius of convergence one works for a lot of things, and that helps give a coherent treatment of analytic combinatorics at this level. So here's the theorem. The idea of this theorem is that the function 1 over 1 minus z seems to arise a lot in the combinatorial constructions that we develop. So this is 1 minus z to alpha power, where alpha is not necessarily an integer. The only restriction is that it can't be a 0 or a negative integer. And it so gives us, in some sense, it generalizes the ratio on that I did before, where g of z was a polynomial. Now it's 1 minus z raised to alpha power. Coefficient of z to the n and f of z over 1 minus z to the alpha is asymptotic to f evaluated at 1 times n plus alpha minus 1 choose n. And that's asymptotic to f evaluated at 1 n to the alpha minus 1 over gamma of alpha. Gamma of alpha is a constant I'll talk about in a second. And I'm not going to go through the proof now, because most people are just going to want to apply this theorem, not prove it. But it's not that difficult a proof. Really, it's a convolution that involves a generalized version of the binomial theorem. And also, since the thing converges, the sum of the first n coefficients converge exponentially to f of 1. That's the quick description of the proof of the first part. And then the second part is standard asymptotics, just using the definition of the generalized binomial coefficient and this function, the gamma function. If you don't know what the gamma function is, here's just a real quick summary. It's a way to generalize the factorial function. And it plays an important role in analytic combinatorics and the analysis of algorithms, because it arises in transfer theorems just like this one. So for real z, if you define this function, gamma of z equals integral from 0 to infinity, t to the z minus 1, e to the minus t dt. turns out that function has the properties that we would want in generalizing the factorial. For example, gamma of alpha plus 1 equals alpha times gamma of alpha, just like n factorial equals n times n minus 1 factorial. And then if you work it out, gamma of 1 equals 1, so gamma of n plus 1 is exactly equal to n factorial. So for integers, it matches the factorial, but it always satisfies this property for any alpha, and so gamma 1 equals 1. And then one that comes up really a lot for us is gamma of 1/2. If you want to compute gamma of 1/2, so take z equals 1/2 in there, and then you get something like the normal, and then you compute it to be the square root of pi. And so gamma 1/2 equals square root of pi is a value that we want to know, because we apply this thing with alpha equals 1/2, the square root of 1 minus z. So that's a transfer theorem that works whenever we have a convolution of some function with 1 minus z to the alpha, and that turns out to come up a lot. And just a little more generally, if the radius of convergence is bigger than rho, and if a rho is not equal to 0, so just applying this to z over rho, plugging in z over rho in this theorem, then we get slightly more general. We do 1 over 1 minus z over rho to the alpha, and that pulls out a rho to the n in the asymptotics. And that's just an elementary calculation to see where that comes from. So that corollary is the one that we'll really be interested in. So that's the theorem. If we have a generating function of that form, we know the asymptotics. And that applies to the two major problems that we've talked about so far in this lecture. For Catalan numbers, so t of z equals 1 over 2 of z, 1 minus square root of 1 minus 4z. So there's a tiny complication because the first term has to cancel out. But ignoring that, what we're using is alpha equals 1/2 in this. Alpha equals minus 1/2. So that's 1 minus z over rho to the minus 1/2 in the denominator. That's square root, and rho equals 1/4, so that's square root of 1 minus 4z. And then f in this case is just a constant, just the half out front. And so we wind up needing gamma of minus 1/2, and then that's 2 times gamma of 1/2, just because gamma of alpha plus 1 equals alpha gamma of alpha, minus 2 square root of pi. Well, you plug it all in, and then maybe it's easiest to think about it by just multiplying both sides by z. And then apply these exactly. It's not hard to finish the calculation to show that this transfer theorem immediately gives us the asymptotics of the Catalan numbers. So one transfer theorem to get the generating function, another transfer theorem, the analytic one, to get the asymptotics of the coefficients. And this same theorem works for the derangements problem. So number of generalized derangements, we had this complicated function. Not so complicated with this transfer theorem. Now we have alpha equals 1, we have rho equals 1. Our function is just e to the minus z. So all we need to do is evaluate f at 1. That's e to the minus 1 minus 1/2 up to 1 over m. That's h sub m. That immediately gives the asymptotics. E to the minus h sub m. So two problems. That the first one, a lot of calculation to get there. Second one, we don't even know how to get there. Immediately through this analytic transfer theorem, we can get the result. And this is just really just the beginning. What part 2 is going to be devoted to is the idea of really universal laws that we can get from transfer theorems based on complex asymptotics. And I'll just talk through one. There's a lot of technical details just to give you some idea. if you have a system of combinatorial constructions where you have a bunch of classes and they're all interacting, those operations indicated by op0, op1 up to opt, those can be sequencer or sum or product operations. You can create a whole linear system of combinatorial constructions. So a very simple special case is the binary tree one, where you get t on one side and z times t on the other side. You could have a much more complicated thing, a cycle of binary trees of sets of, well, not those, but linear combinations of combinatorial classes, a whole system of combinatorial constructions. Those immediately transfer to a system of generating function equations with the symbolic method. Well, that's good, but those generating function equations might be quite complicated and difficult to solve. But in fact, there's a method called Grosvenor basis elimination that reduces those all down to a single generating function equation. And not only that, there's a theorem called the Dermota-Lally-Woods theorem that shows that there's an explicit solution to that equation. That equation's got the square root, and this is in the complex domain, and there's a process called singularity analysis that immediately gives a simple asymptotic form. So any combinatorial construction is asymptotic to a over 2 square root of pi n cubed b to the n, where a and b are constants that we can explicitly calculate from the construction. It's an amazing universal law. And you can find in older mathematical literature hundreds of papers that come up with these kinds of results that this one process covers. And that's just one example of universal laws that we see in analytic combinatorics. There's many more. So that's an introduction to coefficient asymptotics.